Um, all right, let's go ahead and get started. Hi, everybody. Welcome to the first session of the nuclear physics mentoring program. This is a little different, perhaps, than what you originally thought. And so it's also different than what I and my collaborator, Andrew Jakura, he's actually Dr. Andrew Jakura, but I'm not going to call him Dr. Andrew Jakura. So I'll just call him Andrew. This is different than what we originally intended. And the reason is that when we started this mentoring program, we wanted to give the opportunity to people like you that want to be scientists to be able to work with people in the field and get a little bit of taste of what we're doing. And you can perhaps join in some research project. And we were a little bit overwhelmed with the number of responses that we got. So between Andrew and I, we got something close to somewhere between 150 and 180 applicants. And it was just a very hard decision to make of who we could work with. We certainly couldn't work with everybody at the same time. That seemed kind of crazy. And so we needed to make really hard cuts. And we didn't want to give anybody we wanted you guys to have some level of opportunity, and we didn't want to let you miss out on the opportunities that we could perhaps grant you. And so we did the thing that we thought was crazy, which is essentially work with all of you. And so today we're going to explain how this is going to work to some extent, and give you a sense of what we have planned. And yeah, that's a plan. So let me start sharing my slides. And what I'll do is that I'm going to start by introducing Andrew, and I'll say a couple words, and then I'll let him introduce himself. So as you already know, I am a professor at ODU. I'm also a staff scientist at Jefferson Lab, which is a national lab. Is a nuclear physics facility, which is within the umbrella of the national labs in the Department of Energy. Here's the image of J Lab. Here's an image of Jefferson Lab of ODU above. Sorry. And so my collaborator Andrew, I've known him for, I don't know, 5 years now, maybe.
Yeah, about 5.
Yeah. So he got his PhD from Indiana University in 2019. And then he came to work with us at ODU and Jefferson Lab as a postdoc. Postdoc is short for postdoctoral research fellow. These are really great positions where people that have gotten their PhD, so they're already an expert in the field, right? They've written a dissertation, they publish papers on the field. They can, as a postdoc, they can continue doing the research without having to do teaching. And so they are just a full-time researcher. And so Andrew's doing this with my group here at ODU and Jefferson Lab. He's been doing that for the last couple of years. We've written a few papers together, and we're working on many more. I don't know how many papers we're working on right now.
A lot.
A lot. So that's good. He's been productive, and we really enjoy working together. And so we figured it would be fun for us to join forces in this endeavor. Originally, some of you were going to work with me, and some of you were going to work with him. We figured it would be more fun if we work on it together. And I'll just say that he is, as of recent, he's an award-winning physicist. He got an award for a postdoc award through the JSA, which is the agency that runs Jefferson Lab. And so these are postdoc. This is an award that is given to a single person each year to be able to support the research program of somebody who's doing a postdoc. And so he was an award winner this year. So maybe I'll stop for a second and I'll let him say some words, and then I'll jump into some administrative aspects of these meetings. So
Thank you, Raul. Yeah, I mean, it's the research that we're doing here is quite fascinating to me. Um, Examining nuclear reactions from the fundamental principles of physics, which Raul will explain in a little bit, kind of the background. Um, I can I enjoy discussing this work. I'm looking forward to discussing with you all on various aspects of this and kind of showing you what what it is we do in modern nuclear physics. At least the research we're interested in, what it involves and what our goal is. Um, I see there's some questions. My doctoral thesis was on scattering theory for multiple hadron systems. So a hadron is it's a class of particles which undergo strong nuclear interactions. Specifically, I was and still am interested in what happens when you have three of these hadrons interacting with each other. We call this a shorthand 3-2-3 scattering, which you'll hear all about since that's mostly what I talk about nowadays. Um, and the goal is how to connect the kind of basic principles of strong nuclear physics from the fundamental theories to scattering processes, so scattering or reactions of three particle systems. It's something that I'm interested in. I know Raul is interested, and hopefully we can kind of share with you all this kind of general interest for us, why it's important, and kind of give you at least a preview on to the basic physics that you learn in your quantum mechanics courses and in various other physics courses, and how can it be applied to really modern cutting edge research. Um, yeah, I think that's all I have to really say about that aspect. Yeah, so looking forward to talking with all of you. And I see we have another question about the chat. Right now, maybe Raul will explain about this, but I think if you have questions, throw them in the Q&A. The chat is reserved for full participants, which I guess Raul will explain more in detail.
yeah, that's right.
Yep.
Yeah, we'll touch on this. So okay, so maybe something that I was going to touch on that already the question by Shivan is asking this: is there any prerequisites of having taken any particle physics? No, we in fact don't even require you to have taken. Some of you are still in high school, some of you are in college, and some of you may have already taken quantum mechanics. We're not assuming any of that. So that we're gonna we're gonna and to have some, maybe just to give you a little bit of evidence, empirical evidence that we're able to do this, right? We've recently both co-authored a paper with a high school student who had not taken quantum mechanics, and he was able to contribute to a research project that that has been recently published. And I've worked with a few undergraduates, some of which hadn't taken quantum mechanics when they started working with me, and they've been able to contribute to our research. And so we'll give you basically some bits of information. Some of you will be able to digest it at different, I mean, everybody's going to digest it at different levels. And eventually we'll start perhaps separating you guys into pockets depending on your different levels of understandings. And then we'll try to work with each one of you somewhat differently. We're going to discuss how this is going to go. So if this is a question that you have right now, maybe just hold off for a second. In fact, let's jump back in to my slides, and I'll basically start talking about the administrative sides of this project. So, okay, so you're in the Zoom link. You're already in the Zoom meeting, so great. But this is also being casted on YouTube. So if you're on the YouTube page, that's perfectly fine. But if you want to join the meeting, here's the link. So maybe just take a screenshot of this. Also, the videos are not only going to be casted of these meetings are not going to only be casted on YouTube, but also the recordings will be posted there. So if you want to, if you want to check it out later, here, I'll put this in the chat. I'll put this link on the chat. So if there's something that we say that goes a little too fast and you want to cover it again, you can just check it out later. There we go. So I put on the chat for your convenience. And if you haven't checked out our YouTube page before, go ahead, go there, and I would encourage you to subscribe to it so that you can follow the videos that come out. We're gonna have weekly meetings. I think this date works best for us and for most of you. It turns out that the time doesn't seem to work for a lot of people. There's a lot of people that are in India and so, or in Asia in general. And that time doesn't, the time that we're hosting this is a little too late for them. So we're gonna move the time for 10 a.m. and we'll confirm this via email. So we're gonna move this meetings down by 3 hours from now, okay? We'll confirm this with our team that is hosting these webinars and make sure that they can host it then, okay? Then we have, so this is gonna be our meetings. We're also gonna ask you to start writing weekly reports. These are reports where you give a little summary of what you've done that week and what you've learned about. It should include some descriptive text, and I'll explain some of these details as well as any meaningful figures and graphs that you've generated. They should go there, okay? Imagine that what these reports are gonna allow you to make is a little portfolio of your contribution. And at the end of working with us, hopefully you have a portfolio of things that you've learned and that you're able to do. And this should be useful not just for you, not just for us, but imagine then that, you know, hopefully we'll teach you some skills that will allow you to work not just with us, but other scientists around the world. And so if you have a little portfolio that is already saying like, look, I've learned to program, I've been able to do complex analysis of this kind, I've been able to study these reactions, that will make a strong case for you to be able, you know, for these scientists to be able to take you seriously and open up doors for you. So that's what we want to try to get you, okay? So the long-term plans are roughly as follows. First, we're going to give you a mixture of lectures and assigned projects, where we're going to give you short-term projects, mostly numerical in nature, some of them mathematical in nature, depending on your level of math and programming. The lectures are going to be focusing on aspects of, you know, math and programming, of course, but they're going to be centered around nuclear and particle physics. In this period, we'll hopefully get a better sense of your academic background. You put a little bit of information in the application, but that's not enough to discern where you're at. And ultimately, you might end up working with one of us, or as I already suggested, perhaps what we'll do at the end of the day is try to connect some of you with researchers across the world. We have collaborators in different continents, in different parts of the country. And we know many, many more nuclear physicists that I think would be really happy to work with talented, driven young folks like yourself. And so, you know, that opportunity hopefully would open up after working with us. We are also going to have weekly casual meetings, and these are going to be hosted on Thursdays around noon our time. We'll send you information about that later. And we're going to probably have a chat where we can have a little more back and forth. We have a slight preference towards Skype, but some people prefer Slack. I don't know if we made a decision about this. Andrew, do we know what the age requirement is for Skype?
No, I can look into that right now.
Okay. So Slack only allows for folks that are 16 years and older. I don't know what's the case for Skype. There's some of you that are a little younger than 16. So yeah, somebody asked about Discord. I use Skype all the time, and I can use Slack. I see somebody says that Skype is banned in some countries. That's unfortunate. So we can certainly try Slack. I'd rather not have to use yet another platform like Discord, but we'll send you the details once we set it up. Is there any other constraints out there that people they might not be able to use Slack? Is everybody able to use Slack if we choose to do that?
Skype says 13 is the age limit, but if it's banned in some countries, then it's probably not ideal.
So okay, so people are asking about where the meetings are going to be webinars or they're going to be more interactive. I'll get to that in just a second. In fact, I'll get to it right now. For you to be able to be in these meetings, you need to have sent us the photo release form signed. It has to be signed by either you and or your guardian if you're underage. We've received lots of you that have said that they, that have signed these forms to help us sort this out. Can you send us right now in the Q&A box your name, email, and or your guardian's email so that we can go ahead and start confirming who has signed these forms, send us these forms, and we'll start moving some of you into the panelist section. All right, so people are emailing. All right, this is Andrew. Do you maybe want to start sifting through this and checking, confirming that they've sent us these forms? I put some of the forms in our Dropbox folder, the one that you and I have access to only, and maybe as you confirm one by one, maybe share the email with Kevin, and then we can start maybe moving, or either we start clicking. What we can do is you can actually click on the participants if you're a co-host. Kevin, does Andrew have permission to move the participants from?
I'm sorry, what was that?
Sorry, I was asking, does Andrew have permission to start moving attendees into the panelist section?
Oh, I can grant him the access. Yes.
Okay. Well, so we're gonna do it one by one, and this is gonna take a little bit of time. So I think what Andrew will have to do is look at the emails that are being put in the Q&A box, confirm that we've gotten those forms from them, and then he'll send you those emails so that these are people that will be able to be on the panelists section going forward, not just today, but they'll be able to be panelists going forward. Does that sound okay to you, Andrew? The work lies mostly on you.
Yeah.
Okay.
Yeah. I'll start going through and check marking who's here.
Okay. That's good. Andrew's dogs are a little more lively than my dogs, so sometimes you hear his dogs. Okay, so please be patient with us as we start moving some of you into the panelist section. And so if you sign these forms, you'll be able to talk to us, and you're going to be recorded. It's going to be posted live. You can keep your camera on or off. That's up to you, whatever you feel comfortable. So if you feel more comfortable with your camera off and not asking questions, that's perfectly fine. But you have the opportunity, you have the chance. Okay.
Raul, do you want me to start moving them over now as I go through this list?
Yeah. So let's say, for example, Amir, right? Amir gave you their email, right? And name. So if they've given us the release form and you check it, just send that text send the email directly to Kevin under the chat, and then he'll promote them to panelists. Okay. And this way, Kevin has this emails forever. So then next time that we have these meetings, they can be automatically moved into a panelist section.
Okay.
Yeah, all I need,
Also,
just to confirm that, all I need is just a list of email addresses after they get admitted.
okay.
You guys could provide that list to me, then I could add all of them there. And then next time they use the same email address and they would be just fine logging into the panelist.
Very good. Yeah, so you choose, Andrew. You can promote them yourself or pass that email address to Kevin before or after. And one thing that is important is that to make things smoother, you should be giving us your email that you've used to log into Zoom. Okay. So otherwise, it's not going to be automatic in the future. All right. All right. So that's about the form. I see that somebody has so I see that there's question already about the form itself, which is this Annex 1 form or Annex 2 form. Anonymous is asking, I think it's Annex I or Annex L. I think that their concern is about the unfamiliar conditions. Basically, these are conditions saying that so for this is saying that you're able to be recorded and there won't be any issues afterwards. With the other form, it's basically just saying that you're comfortable with participating in any sort of activity within the university, Old Dominion University. Most of it doesn't apply because this is going to be a virtual event, and we're just going to be chatting via this way. So a lot of the text is unfamiliar because it's not necessarily relevant for this case. And so you're welcome to read it with a guardian or somebody that may be able to consult you on the language. But considering that this is a meeting that is just going to be happening remotely, most of the concerns that are flagged there won't be relevant. Okay, so hopefully that answers your question. All right, so while Andrew continues to sift through the 80 plus messages, I will continue giving you a little bit of admin background. So I see another anonymous asking, what is the advantage of Annex L? Well, Annex L is the photo release form. And so you will be able to be in this chat with us, talking and interacting. As long as you don't sign that form, we'll keep you as an attendee. And so you'll be able to send questions via the Q&A box, but you won't be able to talk to us. So if you don't want to talk to us, that's fine. So you can stay behind the barrier. We can activate the chat, but we won't be able to hear your voice. And somebody asks if they should write their email and name in the Q&A right now. Yes, go for it. Okay. Do you have your somebody asked if they have to have their camera on for this? You don't have to have it on. No, it's not a requirement. We can have it off. I'm just showing mine for transparency so you can see what I look like. I don't need to know what you look like. So if you're not comfortable with that, that's perfectly fine. We're trying to have something that is flexible so that everybody feels comfortable and feels welcome and heard, but we don't want to force anybody to, have to do anything they're not comfortable with. Okay. Hopefully, I think those answers most of the questions. I'm not seeing other questions. And Sain says that 10 a.m. does not work for you, for Sain. What time zone are you in, Sain? Sain Mothupi. I love your name. And yes, you would be able to see the meetings afterwards. So can you tell me which time zone you're in? Miguel asks, if as the course continues, will there be different groups assigned? Perhaps, but not for a while. Okay. All right, let's keep on going. So the weekly reports, you're gonna be able to provide them in the Dropbox folder, which I'm gonna put on the chat. I've emailed this to you already, but I'll put it in the chat one more time. This is a folder that looks like what I'm showing on the screen. Inside of it,
Raul, I think you sent it to just the panelists. You need to send it to attendees as well.
Oh, yeah. So this is what we have Andrew around. Yeah, I see. Appreciate it. Thanks, Andrew. So you can go into the Dropbox folder and make your own folder with your name and last name separated by a little line, a little underscore. You could put a dash if you want, but I prefer underscore. Within it, you should make a folder for each week. So we're in week number 1. Okay. So go ahead and do that. And then each week, you're going to have to put a report on what you learned about that week, what you did that week. You're able to not just put a report, but you can put in code or any material you wish to use, figures, whatever, that can all go here. And the weekly report, as I said, it should be just a summary of what you've done and learned about. You can have some descriptive text, some meaningful figures. So here, for example, I said on week number 1, we talked about quantum chromodynamics. You see, it's a fundamental theory of gluons, blah, 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 blah. It's, et cetera, et cetera. You can put as much text as you want, okay? It doesn't have to be a thesis. The more formal, the better your writing is, the more professional your writing is, the better, because you practice that, right? That's a good exercise. I see also that we have people from, all over the world. Not everybody's a first language speaker in English. I'm not, right? And so the more we write in professional English, the better we get at it, right? And so you want this to be, it doesn't have to be super formal, but somewhat professional, okay? So I see that Aditya asked if I can elaborate on the weekly reports and the things that should be included. Does this clarify your question, Aditya? Is this enough, or do you need more? Do people have any more questions about the weekly reports? They're mainly for you, so that you see the progress that you're making, and then eventually you'll be able to piece them together into what could be a portfolio later on that you can then present to people and say, look, this is what I've done. I'm interested in working with you. This is, you can enumerate the things that you've learned, right? How do you add a folder on Dropbox? You can just go to your Dropbox. So it depends on the format that you're using in Dropbox. I download mine to my desktop. So let me see. So I download it to my desktop and then I right click it and then I can make a new folder. So it's very easy there. On the website, it's a little bit different. There. Give me a second. Let me see if I can do it on the fly. I haven't done this before on the desktop. I mean on the website. So here, I think, yeah. So if you're on the website and you should have access to edit, you can make a new folder and then put here. Oh, that's an interesting question. Create folder. Oh, let's see this test. Oh, sorry. Do you know how to make a folder from up here? Create new folder. No.
That doesn't do it in the
Andrew.
create folder.
Yeah, but it seems like I had to specify who can access it. Only you or specific people? It seems strange.
Yeah.
Are people able to access the folder, the Dropbox folder? Well, how about this? If people
I know I looked at that folder earlier.
Do you want to try accessing it and making a folder in your own on your side and see if I can see it?
Yeah, let me do that. Do it this way. Nuclear mentor.
All right. Well, if you can't make a folder, give me a little bit and I'll do it. I'll try to fix this afterwards, but hopefully he can.
Yeah, so I just made it. Try to refresh.
It's going to take a second. Nuclear_mentor projects.
Yeah, that's.
It has an updater for me. Do you put one that is at this level?
It just says mine. Yeah, at that level there.
Okay.
I'm not sure.
It might take a little bit. All right, we'll go back to this, but hopefully if you're not able to, I see somebody saying that this is only good for sharing, for seeing.
Can you try just backing out and going back into that folder?
I'm also seeing it from.
Yeah, I don't know. I'm confused.
Copy link. Oh, I see. The link, yeah, Philip is right. The link that I made is only for viewing. All right, I think what we'll have to do is, I mean, at least one solution to this. Link for viewing settings. So one solution to this is once we have all your emails, what I could do is just send this to everybody via email. And so I can just copy your emails. I'll do that once I stop sharing my screen, okay? So hopefully what you will get is an email from Dropbox giving you access to this, okay? So I'll do this afterwards. I'm not gonna do it now because I'm sharing my screen and I don't wanna expose anybody's emails. Does that sound okay? So I'll do that shortly. All right, so let me start jumping in. So we are assuming that you have some programming experience. It's going to be necessary for the kinds of things that we're doing. Not everybody here has some programming experience. That's okay. You can catch up, and the best way for you to catch up is essentially to defocus a little bit on the content that we're going to be providing here, and instead focus on the content that we've been teaching in our Python for STEM course, which started earlier in the summer. The videos, if you missed the class, all the videos are available in the REYES YouTube page. And so you can go there and just watch from the beginning. Okay. So that's what I would encourage you to do. And so if you haven't been participating in the Python for STEM course, the first step that you should do is send us an email at pythonforphysics@odu.edu. That's Python for physics@odu.edu. And you will get an auto reply with all the links that are necessary for the course. And so my advice is that you work through all the exercises that are there, and I'll put the email for Python for physics there, and make sure that you're able to do those exercises and then come back to the things that we're going to be doing here. Because here we will be jumping more into some physics, and the computational stuff is going to be slightly more advanced than what we do in Python for physics or in Python for STEM. So yeah, hopefully that only applies to a handful of you, but I think it's going to be necessary. Okay. So somebody says that they were able to make a folder. I still don't see them. So we have a problem. We'll fix this later. Okay. All right. So maybe here's a good time for general questions, administrative questions. Are there any administrative questions that haven't been answered yet? This is your time to ask questions. So I see. How long are the classes? We're going to try to keep them to within an hour and a half or so. Otherwise, we're going to get too tired. And so it could be like an hour and a half. So that is going to be a little bit closer to an hour and a half. Do you have to write a report for this week? Yeah. Are we going to use Python for the programming part throughout this program? Largely. You can do things independently, but Andrew is going to start showing you material that he has already generated to help you get started. And this is going to be done in Python. If you choose to use another language like C++, getting familiar with Python is going to be useful, but you can do everything in C++, in fact. So what is going to be the difference between the Monday and Thursday meetings? The Thursday meetings are going to include mentees from other projects as well, not just your own. And it's going to be a little more casual. What type of files should we upload? Are PDFs okay? Yep, perfectly fine. I put a Word document, anything that is useful for you. Josh says that they were able to open the Dropbox link. That's great. I'll give you all permission to edit later on. Will there be an exam? No. And will you receive what will you receive as a proof that you're able to do things, I guess, is a question. Well, so we are going to have certificates for the program, for the mentoring program. These will be given at the end. So you'll have that as proof that you participated in this. And we're going to use your weekly reports as a way for us to confirm that indeed you were participating in this program. Should we forward all the forms to your email addresses? Yes, Philip. So if you haven't signed them and emailed them yet, please send them to rbriseno@odu.edu and ajekura@odu.edu. If you have any questions about the mentoring program, email us both. Always email us both. Otherwise, it's more likely that you will miss a response. In fact, I would appreciate it if you only reply to the first set of emails that we've sent you instead of sending us separate emails, because sometimes you send us separate emails and we don't necessarily recognize your emails, and sometimes the titles don't help, and so they just get lost in the sea of emails. So just reply to the original email that I sent you a while back, which was titled, let me see what it was titled, that I sent you. I think I sent you last week. The one that is titled Regis Mentor Program Project / Nuclear Physics. Okay, so if you email us that, it's going to be much harder for us to miss your emails. And you have to be a little patient with us because I'm getting over 100 emails in a matter of days. So it takes a while for us to get back to everything. But what time should you upload the weekly projects? Whenever you get it done, whenever you have time, no pressure. The timing after August 25th might change, but we'll keep you posted. We'll confirm this weekly by week. Will going through Python for physics affect your progress here? No. I mean, no. What matters is that you're doing something each week. And so if you have no programming background and you use this time to learn about a little bit of physics, and in doing that, you're also learning about Python, you're taking a class on Python for physics or Python for STEM, put the progress report. That's all you have to do is just be doing something that is related to this, right? And so it could be learning Python, it could be learning programming, it could be learning about math and physics, all right, and particle physics. So that will go into your into your progress report. What is the desired output of the program? The desired output is that you learn some physics, some programming, and you can explain this to, just at least give us reports that explain that you've done this. So somebody sent the annexes to Regis, the Regis email. No, you should be sending it to us. Everything should be to us, and it should be a reply to the original email that we sent you. Just reply all to the original email. Reply all, not just reply. All right. What topics would be studying in a series of lectures? Well, nuclear physics, we're going to jump into it in just a second. So we'll be covering this. You don't need to learn anything outside of this lectures that I will be giving you. What is the number of expected hours that you will have to invest in the project? The number of hours that you want. Really, this is about you doing as much as you can and want. And if you make tremendous progress, that's wonderful. If you're learning a little bit, that's better than nothing. So that's great. Will we have one meeting per week? Yes, most weeks. Andrew and I may be taking a vacation soon, not together, but at the same week. And so we might need to take that week off. How do we use professional language for the reports? That's a great question. So you want to avoid having, basically the language has to be at least grammatically correct. You want to avoid abbreviations. You want to start mimicking some of the language that we use in our lectures. I think that's it for now. It just, it doesn't, it's, it's just language that is slightly different than, it's closer to what you would see in a textbook, and less so than the language, it's a little less like the language you use, say, with your friends. Can you use C++ instead of Python? By all means, go for it. After all this, will you be working with one particular mentor? Yeah, perhaps. And it might be more one-on-one. Do we have any resources requested to learn about nuclear physics and particle physics? Not at this moment, no. Will you have to write a report on the whole project at the end? Perhaps. Would there be something like a publication? Not yet. That's far from the reality. It's not impossible, but we're not there yet. All right. So we got another question about how would the final project be assessed? So what we're planning to do is, after months or perhaps a year, we will, once people have developed more specific skill sets and there's some meaningful outcome, then we'll invite people to perhaps give presentations. And so that's what we're thinking about. Okay. Okay, so we have a question from Josh about general about how do we approach any research project like ours? How do we select the topic, and how do we approach it all? Well, you're going to learn about this here. Basically, the way that we all learn is first by working with somebody who is an expert in the field and learning what they're doing, getting some guidance, learning some tools, and then getting familiar with the field, and then start asking questions ourselves. Once we have the tools to be able to answer those questions, then we can start contributing. So that's what you're going to be doing. Yes, you're supposed to submit a report on today's meeting. You emailed Dr. Briseño, but not Dr. Jacora. Yes, you should always copy Dr. Jacora. And like I said, we just want you to reply all to the original email that we sent you. Don't send a separate email, okay? How long is the program expected to last? We don't know yet. It's going to be at least 4 weeks, but it might go longer. So we don't know yet. All right, I think that's enough for questions. I've covered most of the questions. Oh, when should you upload the weekly report? When you have it ready. If it's next week, if it's 2 weeks from now, that's okay. It's just something that at the end of the day that says that you've, the sooner the better, of course, but like it's something that basically says that you've been learning about this stuff, okay? All right, so I'm gonna jump in. And so let's start moving away from administrative stuff. We took almost an hour on that, which is fine, it was needed. So I'm gonna start lecturing about nuclear physics, scattering theory, and yeah, which is what we're going to be learning, what we're going to be discussing in these projects. Okay, so all right, so some of this will be knowledge to people that have taken my Python for STEM course, because I talk about this. Some of it won't be, so some of it will be new to them too, so just bear with me. And let me start zooming out. So okay, so physics is really trying to, the major goals in physics is trying to understand what are the key players in nature, namely what are the constituents that describe everything that we see in nature, what are the guiding rules to which they interact, and how are these objects come in together and piece together to form more complicated phenomena that we observe in nature. And the guiding rules are essentially are described by fundamental forces. So we've been able to discern that nature, if you strip it down to its simplest constituents, they interact in a finite number of different ways. Okay, and these finite ways in which they can interact are known as fundamental forces. So far, we know there's 4. Okay, there could be more, but right now we know there's 4. One is gravity, which is described by the general theory of relativity by Einstein. And this, of course, describes how massive objects interact. Another one is electricity and magnetism, which at the fundamental level is described by a theory known as quantum electrodynamics. It's in fact the most precise, it's the theory that has the most precise predictions in all of science. Okay, so this is a huge, remarkable success of the last 100 years. Then there's the strong nuclear force, which is described by a theory called quantum chromodynamics, and this is what I'll be discussing largely. Then there's a weak nuclear force, which is responsible for radioactive decay as well as other phenomena. Okay, these three. So the general theory of relativity essentially describes the massive objects that are not small. These three describe the interactions of subatomic particles. And in fact, if you grab these three forces, along with the known 17 fundamental particles in nature, these combine together to form what is known as the standard model of particle physics. And this is what we study. And the most complicated sector of the standard model, the most mysterious sector of the standard model, is the strong nuclear sector. And that's the one that we focus most of our time in these days, because although we know that there exists a fundamental force, we don't know how to tease from it, or we know that there exists a fundamental theory. We don't know how to tease from it in general phenomena that we see in nature. And so that's an outstanding challenge, and we've been able to chip away at this challenge, and that's what our research focuses in. So a strong nuclear force has different manifestations of scales. It's the force that makes atomic nuclei possible. Is the thing that attracts protons and neutrons into, say, things like helium, which is what this cartoon is showing, as well as other states like carbon-12, oxygen, etc. And so these are bounded together by the strong nuclear force. But it turns out that the strong nuclear force is even more complicated than that, because these objects, these neutrons and protons, are themselves made out of other particles that are themselves even smaller, known as quarks and gluons. In fact, to this day, we don't know the size of these particles, and it's assumed that they have no size. It is assumed that they have no structure. In fact, all the fundamental particles, all of these are assumed to be structureless, meaning that they're point particles. They can have mass, but their size is zero. Okay, this is what a fundamental particle means. Unlike protons and neutrons, which have a size, they're tiny, but they do have a size, right? And so, as far as we know, fundamental particles just don't have a size. It could be that they do have a size, but we don't have a resolution scale that is fine enough for us to be able to discern their size. Okay. So nuclear physics these days is interested in everything from the fundamental building blocks, quarks and gluons, all the way to the things that they can then construct, namely atomic nuclei, as well as like other exotic states of matter. And so this theory, which is called quantum chromodynamics, and for short, we'll be calling it QCD. I've already said this, that it's a fundamental theory of the strong nuclear force, but it's hard to overemphasize what fundamental means in this context. And the way that I like to think about it is that fundamental means that it's been etched into the cosmos, that is written into the universe, these rules. And what is written is essentially this one line. This one line is for those of you that are taking physics, this is the Lagrangian. In fact, it's the Lagrangian density of theory that describes all the interactions between quarks and gluons. And what is remarkable is that it's a tiny little line. It's so simple to write down. But this equation is believed to not just be essentially written into the universe, but it's been played a role in all instances and in all parts of the universe. And so it's been essential from the beginning of the universe, where the universe was just a hot soup of quarks and gluons. And that's the original state of the universe. It was just a tiny little soup of hot quarks and gluons. Also, there were electrons. Okay, these conditions are in heavy ion collisions. These are collisions where in particle accelerators where the ions like gold are being accelerated. So the like gold nuclei are accelerated to such high energies that although they're spherically shaped, they get flattened into a pancake when they go into really high energies. These are then smashed. They create an intermediate short state that has very high temperature, and it's essentially the same kind of conditions that exist in the early universe. You have essentially free quarks and gluons that are moving around the soup, and then they start to cool off as they start to expand, and then these quarks and gluons start to combine together into bound states of the theory. And these are different types of particles, which we'll touch on, and they then get detected in experiments, particle detectors. But this theory is not just important in the first instance of the universe; it's also the driving force of the evolution of stars, like our very own, the sun. The sun is just basically a huge nuclear reactor, and you're just having nuclear reactions happening over and over again. The result of which is this energy that is being emitted that is keeping us warm and alive. In there, you have atomic nuclei starting to collide and form even heavier atomic nuclei, like carbon all the way up to oxygen. And even at later stages in stars, when the fuel starts to run out, and then eventually the stars collapse on their own weight due to the gravitational pull, they can then lead to these nuclei to smash into each other and form even heavier nuclei, like iron and gold, etc. And these then get exploded. There's a shock wave that takes place, and then these get exploded, and they proceed to permeate all of the universe. And so in all these conditions, you have nuclear physics happening, and it's all being driven by this one equation. Of course, this equation is also responsible for the reactions that we see in experimental facilities like Jefferson Lab, where we're trying to discern the spectrum of a theory, as well as future experimental facilities like the Electron Ion Collider, which was recently approved to take place in Brookhaven National Lab, where what the goal there is going to be able to resolve the inner structure of heavy ions or moderately sized ions even further. Okay, and so this one simple equation is just remarkably important and plays a role in many things. And so maybe a little bit of more understanding of what this equation is telling us. Let me look at my time. All right, I'll lecture for like 30 more minutes and then we'll call it a day. So I've already said this multiple times. This is the theory that describes structures of quarks and gluons. These particles carry a charge-like quantity, just like in charge that particles that interact via the electromagnetic force carry a charge. These quarks and gluons carry a charge-like quantity that is called color. It's a name. Chromo is just it refers to color, right? So the quarks are actually, they don't just carry a color, they also come in different types. Okay, these different types are given the name flavor. So instead of saying types, we say different flavors. It's just kind of silly naming. Okay, physicists can be kooky. We like to have fun, right? And so they name this charge thing, color, flavor for different types. And the flavors, there's 6 of them. They're up, down, strange, charm, bottom, top. And basically, under the strong interaction, they're telling you the mass of the particle. And so they go from light quark masses to really heavy ones. And so the joke that you can make, right, is that different flavors have very wildly different caloric content, right? Because mass is equal to energy, calories at of energy. You get it, right? The gluons themselves don't have any mass. Okay, so quarks are kind of like electrons in this sense. So they carry a spin, the same spin as electrons. They have a mass. The gluons are kind of like photons, which are the photons of the particles of light. And so photons are massless. They carry a spin, which is a spin 1, so they act like a vector. Gluons act like a vector as well, so they're spin 1, and they're also massless. All right. There's something that is very different, though, between quantum chromodynamics, QCD, and the fundamental theory of electricity and magnetism, quantum electrodynamics, QED. Okay. This difference is that quantum electrodynamic, you can, even though you can have bound states of charged particles like hydrogen atom, any molecular state, right, is a bound state of charged particles. You can strip them, right? And you can have a free electron in some place. You can have a free nucleus in another place, right? And you can see them by themselves. That's not the case. And you see electrons all the time, right? Like when you have lightning, so you can see charges flowing, right? That's not the case for quarks and gluons. They're never free. And so this is maybe perhaps why most of you have never heard of quantum chromodynamics in high school, because it's just a very confusing theory. It's very complicated and it's very hard to teach. What the idea is that quarks and gluons are never free. They're always confined. They're always tied up into their bound state. So there's always they're confined, and so this is referred to as confinement, this phenomena. And in fact, they're confined in very particular ways. So they can either be confined they have to be confined in color neutral combinations, meaning you have to have 3 quarks at least, where they have one being red, the other one being blue, and the other one being green, which refers to this charge-like quantity, right? So they have to be in this combination. Or you can have something that is a red and an anti-red, or a blue and an anti-blue, or a green and anti-green. And so you can have 3 quark pairs like this, or you can have quark anti-quark pairs. Just so is, okay? And this is actually an outstanding challenge to understand why this has to be the case, and how do we understand this emerging, and there's many Nobel Prizes to be won if we really understand confinement and what it implies for the formation of matter. So and let me go on. So hidden inside of this equation are not just the quarks and gluons, but it also is the rules on how they interact. And the way they can interact is as follows. So here is the first time you're seeing a Feynman diagram. This is a Feynman diagram. These Feynman diagrams are placeholders for mathematical expressions, but they do tell a nice physics story, which is that quarks, which is a solid line, can interact with gluons, which is this wiggly line. So you can have an interaction where a quark comes in, it fuses with a gluon, and then it goes off in its merry way. Or you can think of it as a quark comes in, emits a gluon, and then it goes off in its merry way. Okay, depending how time is flowing, it tells the same story. Here, so these things happen in quantum electrodynamics, where you have electrons interacting with photons in this same way. What doesn't happen in electrodynamics is the next thing that I'll tell you, which is that gluons can interact with gluons. So they can come in and fuse together into one, or equivalent, you can think about a gluon coming in and then decaying into 2. That can happen, okay? And also you can have 2 gluons scattering off of each other, right? So imagine time is going upwards, or if time going sideways like this, then you can have a gluon that then decays to 3 gluons. That can happen, okay? That doesn't happen in QED, the theory of quarks of quantum electrodynamics. Photons can interact with themselves. And so this is a large separation between QCD and QED, that this can happen. And this leads to dramatic changes in the theory. And in fact, all these reactions are proportional to one constant g, or they're defined by a single constant g. This constant g is telling us essentially how strong these events can, they're telling us the probability that these events will take place. Well, this constant, in fact, is not a constant at all. It turns out that because of these kinds of interactions that appear here, this is actually a parameter that depends very strongly on the energy in which the reaction is taking place. And so here, Q is the energy of the reaction. It's being plotted in some scales, GeV, but it doesn't really matter. And here you're seeing that at low energies, where Q is in the order of 1, going all the way to order 100, this coupling gets bigger, right? But if you go to higher and higher energy, this coupling gets smaller and smaller. And so for those of you that are taking quantum mechanics, what this means is that at high energies, the theory is perturbative, and low energies is not perturbative. And so if you've learned about perturbation theory in quantum mechanics, then perturbation theory assumes that the interactions are small, and they're indeed small at high energy. So all the tools you've learned about perturbation theory are useful here. Of course, this is more challenging than what you learn in quantum mechanics, but that's okay. Basically, the basic concepts they propagate through. But at low energies, perturbation theory completely fails. Okay, why does this matter? Because if at low energies, the probabilities of these is high, as well as the probability of this happening is high, is that you can have now increasingly complex ways for quarks and gluons to interact with each other, which would then it would be hard for us to create some sort of hierarchy on which ways it would predominantly interact than others. So for example, if I wanted for two quarks to interact with themselves, right, I can just say, I'm going to grab these building blocks. I have some incoming quarks, right? Well, a quark can couple to a gluon in one way, and then that can be absorbed by another gluon over here, right? That's the simplest way. And this is, in fact, the simplest Feynman diagram that I can draw where quarks can interact with each other, given these rules, because these are the only rules out there, right? These are just building blocks for me to draw diagrams, right? But if this can happen, also many more complicated things can happen, right? But this is proportional to g squared, while this is proportional to g to the 9th, right? So if g was a small number, this would be a small quantity. But if g is a big number, this could be big. And in fact, the more complicated the diagram is, each diagram represents something mathematical. So the more complicated a diagram is, the harder it is for me to evaluate it. And so I don't know which ones of these will dominate at low energies. In fact, both of them could contribute. And so I would be having to work to drive many mathematical contributions for me to be able to make any predictions of particles interactions at low energies. This is a huge showstopper, a big challenge, because at low energies is where this phenomena of confinement happen. At low energies is where questions about the origins of our mass emerge, where matter gets formed. And so this has led to a historical amount of limitations in our understanding of the consequences of this theory. And so this has limited us quite a bit. Of course, this is not the end of the story, because that would be a very depressing end. So let me tell you now how we're trying to circumvent these historical challenges. So let me introduce you. This is our team at our team at Jefferson Lab. So Andrew and I are part of the nuclear theory group at Jefferson Lab. So Jefferson Lab is an experimental facility, but it has a center for theoretical physics and computational science, computational physics. Both of us are members there. This is a picture that was taken just before Andrew started, so he's not in the picture. I should squeeze him in there. If I would have known Photoshop, I would have probably squeezed him in there. And in there, we have experts of different kinds of people doing all sorts of nuclear physics. But a good chunk of us are working on using supercomputer clusters. And here you're seeing a picture of our cluster, which includes this is the largest and biggest and fastest supercomputer that we have in Virginia is by no means one of the largest investors. I mean, it is among the largest investors across the nation, but not certainly the fastest and largest. And what we are using is a numerical tool, which, let me skip forward actually. Let me bring this. So what we use is a numerical tool that is called lattice QCD. And the idea is that we grab the standard model of particle physics, we shove it into a computer, and we let the computer do the hard work for us. And we make no assumptions about the underlying dynamics and how strong or weak the interactions are. And this is beautiful. This is essentially what we've been missing to be able to tease out physics from the theory, because we don't want to make assumptions how big this coupling is, this G is. We want it to stay as strong as nature wants it to be, and we just want to see, we just want to understand how to tease out information from the standard model. And in fact, the fact that this G coupling is so big has made the strong sector in the standard model, the opacus, is the hardest one to understand. This has been the challenge. And that's why many of us are working out in this direction. There's been other tools proposed in the market, but lattice QCD is the best at resolving these issues. It's the most systematic, is the most costly. It requires the largest computational resources. That's why we need supercomputers, but it is the most rigorous. And so we prefer rigor over anything. And so within JLab, the nuclear theory group there, in particular the lattice QCD, and I'll explain where this word lattice refers to in a second. We're focused on three different aspects. We're interested in nuclear structure, which is the question of how protons and neutrons come together to form bound states, heavier atomic nuclei. We're interested in hadron structure, namely how these quarks and gluons come together to form the states, in particular the proton and other low-lying states. And then we're also interested in what is called spectroscopy, which means, what are the possible energies that these quarks and gluons can combine to form the bound states of the theory, and what are the energies of, what are the possible states and what are their energies. That's what spectroscopy refers to. Let me tell you a little bit of motivation, at least on spectroscopy and nuclear structure. So the questions that we're after is, in the spectroscopy side, is trying to resolve the states of the theory. This is an outstanding challenge, because it turns out that so here I'm showing the nucleon, which is a shorthand for the proton and neutron. Here I'm showing you the simplest state of the theory, which is called a pion, which is a quark-antiquark pair. If you look at the excited states of these, what we want to obtain is the excited states of the theory. For those of you that have taken quantum mechanics, you've learned, you've been able to just obtain the hydrogen spectrum just using the Coulomb interaction into placing the Coulomb potential into the hydrogen, into the Schrödinger equation. And that's a great, if you could do that, you've essentially passed quantum mechanics. If you were to be able to do the analogous thing for QCD, you would be a strong contender for a Nobel Prize. So this is a remarkable challenge. And to see this, you can just look at the excited states, and it turns out that they are unstable. They decay very rapidly. They decay in the order of 10 to the negative 23 seconds. They're among the shortest lived phenomena that we've seen in nature. So they decay to other bound states of the theory, namely more protons and pions of different kinds. They can decay to 3 particles, 2 particles. They just decay very rapidly to very complicated configurations. So this is essentially what we're going to be thinking quite a bit about, is how to describe these states, how to understand their byproducts, and how to study these kinds of reactions where these particles can decay to 2 and 3 particles. That is a lot of what we're going to be thinking about. And there's a lot of experimental efforts, although we are theorists. There's a lot of experimental efforts taking place around the world, including at Jefferson Lab, trying to discern the spectrum. And so a lot of the work that we do is motivated by the experimental searches that are happening. There's still states that are missing that have been speculated to be there. There's been recent discoveries of states like pentaquarks, where you have 5 quarks placed together. Glue balls are still outstanding. These are states that are really exotic, where it could be bound states of just gluons that are tied together. This would be astonishing to be able to find a glue ball smoking gun, because gluons, right? They kind of look like photons, but there's no analog of photon balls. So that doesn't happen. But glue balls could potentially happen. There's just very hard to detect. There's been tetraquarks, where you have 4 quark combinations. There's hypothetical molecular states that would be kind of like atomic molecules, but in very smaller scales. So there's just very exciting kind of phenomena, that some of which have been observed, many of which are still outstanding. On the nuclear structure side, this is the field that is interested in figuring out how, once you put many nuclei together, how they start to interact. One of the basic questions that we've been trying to understand is, how do how do not just 2 nucleons interact? That is very well understood at this point, and experimentally, and we have phenomenological understandings. And we're still trying, nucleons, right, is placeholders for protons and neutrons. One of the basic questions that we're still trying to discern is, how do protons and neutrons interact once you have 3 or more? And here's a simple analogy that I'd like to make, is that life starts to get complicated in general once you start having not just 2 particles, because once you have 2 particles, they interact with each other and they talk to each other, and that's it, right? So there would be some potential that is a 2-body potential, right? Once you start putting 3 particles, then there might be pairwise interactions, but there might be something else, right? And the analogy that I like to make is in conversations, right? Imagine they have 3 people in a room, right? How can these 3 people interact with each other, right? If I were to model their interactions by pairwise interaction, that would mean that A and B talk to each other, right? While C is left to be in the silence and not be able to interact. And the only way that C would learn about this conversation would be because of this pairwise interaction. If the only way that C would learn about this possible exchange that A and B had was because then C would interact with either B or A. That would be a very awkward conversation, right? You would have A and B talking over here. The person would be silenced, and then the information would then propagate that way. Not only would it be awkward, but it would be less productive, right? There's something that happens once you bring 3 people together. The exchange of ideas is much more fluid, that it cannot be described by just pairwise interactions. So there's some residual 3-body interaction that describes how these 3 people, once they're together, something new happens. Some magic happens that makes the conversation even better than it was otherwise, right? Same thing happens with nuclear physics, right? The 3 particles, once you put them together, they're going to interact differently than pairwise interactions. And there's evidence already of this in models. Here's a model calculation for helium, for the determination of the binding energy of states ranging from helium to carbon-12. This is a busy plot, and in one color you see one potential, one model. In this color you see another model, and then here in green is experiment. Let me zoom into one of them, which is the helium calculation. These are just different atomic nuclei. Let me just jump into helium-4. Again, blue and red are 2 different model calculations, and green is experiment. You've seen that they all agree. They give the same number roughly. There's a little bit of fluctuations. That's okay, right? But the point that I want to make is that if you tune off, you just remove the 3-body interaction, the energy that you would get would be off by somewhere between 10 to 20%. Okay. So there would be a large deviation. And so the residual energy, right, this gap is all due to 3-body interactions. And so some of the things that Andrew and I have been trying to understand is, can we predict this gap? Can we really obtain this gap rigorously, directly from quantum chromodynamics? And we've been doing a lot of work to trying to understand this, not just for these states, but many other states. And so You'll be hearing quite a bit about that. How am I doing in time? Maybe I'll skip ahead since I'm running late and I'm chatting too much. So I was going to give you a little bit of introduction to lattice QCD, but I think that we can skip that and come back to it later. Just remind me, we can talk about it some other day. I want to set the stage for what Andrew will be starting to talk about next week. And the idea is that we're going to start talking about how reactions take place in either experiments or in our studies. The thing that we're going to be looking a lot into is scattering amplitudes, which are related to experimental observables. So what you're seeing here is number of events that are happening as a function of energy for some reaction, and you're seeing these rapid rises, these bumps that are being analyzed. You see another bump over here. If you zoom out, if you remove a background, you see the bump even better. In fact, this bump led to the discovery of the Higgs boson, which resulted in a Nobel Prize. And so we're going to learn how to do these kinds of analysis and understand the mathematical formalism behind the description of these reactions and understand where these kinds of bumps emerge and how do we understand them mathematically, okay? And so I figured I would close by giving you a little bit of background on what is being plotted here and what do these bumps mean, just to set the stage. And so the idea is that so basically what's happening in all of these are experiments that are taking place in particle accelerators where you're grabbing particles that are being accelerated to really high energies, you smash them against each other, and then you see a debris of particles that you then detect. And what you're counting is essentially you have control over the energies of the reactions, the energies of the subsystems of the outer products, of the byproducts, sorry. And then you can also detect the number of events as a function of location as well as energy, okay? I'll tell you, if that wasn't super clear, it's okay. I'm going to say the same words again, but in a little slower. So quantum mechanically, what we're seeing, what happens, right, is that if you have enough energy, any event that can take place, depending on the underlying rules of a theory, will take place, right, with some probability, right? And so we build detectors. We build particle accelerators. They're motivated by some physics that wants to be studied, right? And so in general, you want to build some theory that makes some prediction. Then you build the experiment, right? These particle accelerators are accelerating particles to speeds general that are close to the speed of light, right? They're massive particles, so they can't reach the speed of light. These are then smashed against each other, sufficiently high energies that you create a shower of particles. Here's a shower of particles. Obviously, this is not the kinds of particles that are being accelerated. Here's a more realistic picture. So in LHC, so the Large Hadron Collider at CERN, what's accelerated are protons. They're being smashed against each other. There's some exchange, say, of gluons, right? And depending on the energy, what would come out are protons, or you can create new particles, depending on the energy. And then at the end of the day, you're able to isolate these different particles, the plethora of particles that come out using fancy detectors, which I'll explain a little bit, at least like a cartoon of how these work. And here's my cartoon of a particle detector, where you have some particle coming in, some particle coming out. My detectors are just little bin buckets that are connected to a computer that sends a message every single time there's a bin has been filled. And so if particles land here, there would be a signal, there was a particle there. I detected a particle here and a particle there. Most of the times the particles just don't interact. Okay, so they just go through each other and the detectors won't see anything. But with enough times, you'll have enough interactions and you'll start having counting in the buckets. And that's essentially what's happening here. You're counting the number of events. In general, you can count it per bucket or just total number of events for all the buckets as a function of the energy of either the incoming states or the outgoing states. Okay. Ultimately, you want to compare what you predicted with your theory with what's seen experimentally, right? And this is important because without the theory, you wouldn't know what's happening experimentally, but without the experiments, you wouldn't know which theory is right. And so there's a important symbiosis. There's symbiotic. They need each other. And once you have the theory that best describes the outcome, then you can deduce what happened in the crash, because you essentially have pure, complete theoretical control of the reaction. And then you can say, this is what happened, because you've never seen the reaction. You've seen only the byproducts. And so you're then able to, try to discern what happened in the reaction from your theoretical prediction. One phenomena that happens that we'll be talking a lot about is that it's one that is parallel in classical mechanics, which is in particle physics, most particles are resonances. They're unstable, and they're resonances, which means that the probability for them to interact gets enhanced, or for us to detect them gets enhanced near the vicinity of the masses of these particles. This is very similar to what happens in classical mechanics, and when you're either describing strings or the behavior of bridges in some areas where there's large gusts of wind, or the vibration of glasses, you have some frequencies or energies that lead to resonant behavior where the amplitude of oscillations gets amplified. And so what gets amplified in these reactions is not the amplitude of vibration, but it's the amplitude to be detected. Okay. And so it's resonating in that sense. And so here's a little cartoon of how resonances can help amplify your detection. So like I said, most of the time the particles don't interact, but let's now tune the interactions to coincide with the mass of a would-be state, let's say the Higgs. Okay. Then these particles will fuse into this intermediate state that has that particular mass. And then because the probability of that to be created, right? If you have a probability to create that state, it will happen. And then this is now a particle with some resonance, with some mass, some resonance with a mass of m. It will decay, and depending on the properties of the state, it will decay in all possible directions. And so because of that, the enhancement, the probability of these particles to interact gets enhanced, and the probability for you to detect it gets enhanced as well, which leads to this rise in detection of number of events. And so this is a simplistic story of what's happening in your resonances. And we're going to make this increasingly complicated with time, but this is a warm and fuzzy start. We're not going to make it more complicated. We're going to get more rigorous, but it's at least like a warm and fuzzy start to this all. All right. I think that's all I have to say. If you haven't gone to our YouTube page and subscribed, go do so, because a lot of the content, everything will be posted there. So if you miss any of these lectures, you'll be able to see them there. This is a little too premature, but if you're already taking quantum mechanics and you have some experience in, if you want to start learning about some of the things that we're doing in the field right now, you can use this reference. Just search my name. I don't know. Maybe don't do this. It's too premature. We'll catch you up. Let's not get you overwhelmed. So we have time for questions, and I see that we have a lot of people now that have been promoted to panelists. So if people have questions and they want to ask them live, you're welcome to.
So we do have a few in the Q&A and a couple in the chat. Some a bit more kind of fundamental questions, which require some more thought. But for example, Yash asked, why, I guess when you were talking about the electrons and quarks, why is their size assumed to be 0? And then another question, if they don't have a size, does that mean it's an infinite density? But infinities are not allowed in physics, right? So these are some more kind of fundamental in nature. And we have a couple more in the chat, but maybe you can talk about those first if you want.
Sure, yeah. Why don't we see a size? I mean, right now, our best probes into subatomic things are essentially electrons. And so it could be, so essentially you can imagine that right now our scale, or the pixel of the universe is as big as an electron. So if our electrons are ways to see into things by accelerating them to speeds close to the speed of light and smashing against the other things and be able to resolve what's happening, then this is setting the size of our pixels. Okay. And so it could be that they have a size. We just need to figure out a way for us, a mechanism for us to be able to detect their size. Right now, any evidence towards that, it's outstanding. So that's that. What was the other question? Maybe they can tell if that clarifies the question about the size.
The other question had to deal with that as well. Just if they have zero size, does that mean they have infinite density?
Yes. Yeah. I mean, infinite density and like an infinitesimal point, right? So. Any other
There's
question?
some questions on the chat. Esha asks, what does anti-red mean? And then Harshit asks, is it sufficient to measure just the number of particles, or is the type also necessary?
Yeah. To that. Yeah. I mean, so you typically you want to know as much information about the particles as possible. So that will help you get better control on the reaction. The simplest thing is, things like the mass of the particle, right? You want to know not just the mass, how fast it's going, and then the charge, right? And then depending on, most of all the particles that live long enough to hit your detector are very well known at this point. So we know their masses, their charges, their spin, and the different ways that they can interact. And so at this point, you definitely want to be able to have enough resolution in your detector to be able to say which one of the particles that have been already identified is, and then that tells you everything else. What does anti-red mean? Yeah, that's a good question. I mean, we won't. So I mean, essentially, it's just you grab a quark, right? So electrons have antiparticles, right, which are known as positrons, and they carry the opposite charge of the electron. So the charge of the electron is negative, and so the positron has anti-negative charge, also known as plus charge. And so it's a charge that if you add the charge of the electron with the charge of its antiparticle, its total charge would be neutral, right? Anti-red is just that for red, right? You have some labeling number, some label for the different colors, for the 3 different colors, right? And then the anti-color, there'll be anti-color for red, anti-color for blue, and anti-color for green. Just a convention so that when you add them together, the overall color will be neutral. If the color charge, if color is like charge, exists a conservation law for it? Yes. So remember, all the bound states have to be color neutral, and so all the possible interactions between particles is already color neutral, and so all the possible outcomes have to be color neutral. All right. Somebody asked if I could put the slides. I put them up in the Dropbox. And so hopefully people can see this already. I put them under my folder, which I put as Raul Briseño. What is the relationship between amplitude and frequency in measuring energy of a particle? So frequency and energy are closely related. So to first approximation, you can just say that frequency and energy are 2 and the same. The amplitude, what you're measuring what we mean by amplitude is associated with a probability of things to take place. So quantum mechanics is a probabilistic theory. We can't exactly predict what's going to happen, but in principle, what we can predict is all the possible outcomes and assign some weight to each one of those outcomes. And so the amplitudes that we measure is essentially the probability of each event to take place. Okay, and they depend on the energy of the reaction. And so at some energies, you have some probability of something happening, right? But then if you dial more the energy, it's going to happen less and less frequency, right? And that's in fact exactly what I just showed in some of these experimental data. Let me share it one more time to emphasize my point. So here, these are essentially probabilities of things happening. They're weighted by some overall scale. Let's forget about it, okay? So there's some, what gets measured is not just the probability of events to take place. Typically is the number of events, but there's a known relationship between number of events and the probability of things to interact, right? But you're seeing that what is scanned here is energy in some part of the final state, okay? And so what you're seeing is that this probability increases, right? There's an increase of number of events in this region. And so the amplitude is increasing and then decreases and then increases a lot and then it decreases a lot, right? Later on. Same thing here, right? At some low energies, nothing's happening, and then all of a sudden, whoop, a lot of events, and then goes back down to zero. Nothing happens. And that was the smoking gun for the Higgs, which led to the Nobel Prize for detecting it. I don't know what had to. Ah, there we go. Okay. Wow, this last question is Aditya. It's a lot to digest. It's a good question. How do we extrapolate important physical information from inherent numerical data, currents from detectors and times in which the particles are detected? In essence, what are the links between particular observations and that being a certain type of a particle? So you have to have, I kind of glossed over this, right? But ultimately, go forward, right? Ultimately, you have to have a theoretical prediction of what's going to happen. And then what you're trying to see is which theory matches what gets detected experimentally, right? Experimentally, you have some events, right? And these could be, depending on the reaction, you can detect the number of events, or you can also detect the momentum of the particle. You can detect the charge from the curvature of the particle. You can detect the energy. And so between all those pieces of information, right, and having a theoretical foundation for explaining how these particles would behave, right, you're able to say, which one best describes the reaction, right? And then you have to test this over and over and over again, right? You can never prove that there's one theory that describes all the phenomena, right? But you can certainly rule out theories, right? And so you end up ruling out more and more theories until there's one that stands and that describes everything as completely as possible. And then you would say, this is the theory that describes everything as much as possible. Just like we do with gravity, right? We didn't have a proof that Newton's theory of gravity was the right one. We still don't have a proof that Einstein's theory of general relativity is the right one. All you can hope is that things get ruled out, right? And then Newton's theory of gravity has been ruled out because it doesn't describe everything completely or as completely as GR. But you can't prove that GR is the right one, right? It just hasn't been ruled out. Is that kind of analysis bias in some sort, since you're trying to match the data observed to a group of predictions? That's a good psychological question. It's something that plagues the community always, because biases can happen. So now a lot of experiments and some theories, depending on some theoretical calculations, are being done blinded, so that the people that are doing the analysis are not skewed by other existing results. So it is something that is concerning to many. There's always room for biases, right, of different kinds, but it's always hard to discern the biases that exist. There's always systematic errors too, even if you're not biased, right? You can be misguided, or you can be doing something wrong and not know it. And so those are systematic errors. All right, perhaps this is a good time for us to stop. My throat needs a break from all this talking. So what we'll do is that next time you're going to hear less from me and more from Andrew. He's going to start talking about complex numbers, because they're essential for what we're going to be studying in scattering theory. All the scattering amplitudes are complex valued. And we are, in fact, going to be dealing with complex functions that are singular. So this is the bread and butter of complex analysis. And we are not assuming that everybody has taken complex analysis. So that's going to be a lot of what Andrew's going to start talking next week. So hopefully everybody's doing well. I'm glad to see some of you already on this side. Hopefully we can get everybody else to be on this side, but we'll have to require everybody to sign the forms, and it's going to take us a little bit of more time to make sure that everybody that signed the form is here. Okay.
Just as a comment along that line, so with the names that have been given in the Q&A, I have cross-checked them with the documents that I have in my Dropbox folder that is shared with Raul, that I have gotten via email, also with some additional emails that we've gotten throughout this session. If you are not yet a panelist, please be patient. There's still some probably more lingering ones. And if you sent the form just to Raul, I do not have access to that yet, so we'll have to confirm that offline.
Yeah, if you send it to just me, please reply all, include Andrew in it. Okay.
Yeah. But please just be patient, send the forms in, and then we'll get you added hopefully for next time.
All right. Hope everybody's doing well in your corner of the world. I'm glad to see you all, and we'll see you again next week. Okay. Take care.
Thank you so much.
Hey, Kevin, you can close this if you want.
Yes, sir. Just to answer Andrew's question, Andrew, you could just have the Q&A window open, and then you click on one of the entries there, and then you do Control A on Windows to highlight them, or Command A on Mac. And then once you highlight them, you do Control C to copy them, or Command C on Mac.
Yes, I have got that. Thank you very much.
Okay, yeah, there's not much fancy thing to save them. Unfortunately, I went online and researched it. But I did copy the ones that we have right now, if you haven't done so, and I can send it to your email if you want to.
I copied all of them just now.
Oh, you have? Okay, cool. So you are set.
Wonderful. Thanks, guys.
No problem. Thank you. You guys have a great day.
Yeah, you too. Take care.
Thanks.
Bye.
Ciao.